Hello everyone and welcome to today's QCE Units 3 and 4 General Maths lecture. This is our January Head Start lecture and it's designed to give you a bit of an introduction and a head start on some of the content that you'll be looking at this year. You may have already covered some of it in class, but we'll be reviewing some of the key ideas, going through some helpful tips and tricks, and hopefully giving you a bit of a better understanding of some of the Unit 3 General Maths content. My name is Hannah and I'll be your presenter for today. So ATAR Notes offers a wide variety of both free and paid resources that have the goal of helping senior students especially just do the best they possibly can in their studies. These free lectures, which we run 4 times a year, are just one of the resources that we do to help us meet that goal of supporting you as you study. We also have a lot of other online resources like newsletters, articles, like videos, as well as like discussions. And then we also do have like our study notes available as well, which you might have heard of. They're really helpful books as they have like a really concise and helpful summary of all of the content that you go through in class. As well as this, we also have, on top of these study notes, we have like thousands of study resources available on our ATAR Notes Plus website. So the notes for each of the subjects that we have them available for, as well as practice tests for some of the subjects. We're releasing some flashcards as well. There's also a really cool AI answer bot where you can like interactively ask it questions and it'll like use the knowledge from the books and the which is like the content based off the syllabus, and it'll help you answer those questions based off that. So that's a really cool resource as well. ATAR Notes Plus is just a monthly subscription fee if you're interested in accessing that resource as well. But for today's lecture, like we've said, it's for QCE General Maths Units 3 and 4, January Head Start lecture. So we'll be focusing on Unit 3. We'll go over some revision on kind of the first half of Unit 3 and then probably focus a little bit as much as time allows on the second half of Unit 3. A little bit more about me. My name is Hannah. I'm a biology, psychology and general maths tutor here at TutorSmart. I graduated high school in 2021, so I've been through the ATAR system myself. I scored 99 out of 100 in general maths, just lost 1 mark on the external, which I was definitely very happy with. And I'm currently studying primary and secondary education. My major is biology, so yeah, I really enjoy that for work. I get to do lectures like this and share some of my content knowledge and tips and tricks with you guys who are currently about to be going into year 12. So I hope you're feeling really confident about that, and I hope today's lecture gives you a bit of a head start with that as well. So we'll briefly go over what we're going to be covering today. So like I said, focusing in on Unit 3 and each of the different topics. Topic 1 is bivariate data analysis. Topic 2, time series analysis, growth and decay in sequences, which is our arithmetic and geometric sequences, and earth geometry and time zones. Also, keep in mind that we won't be able to cover all of the content, so make sure you keep referring back to the syllabus to see what is expected of you and required of you. Anything on the syllabus could be on your internal assessments and the external. And keep in mind, you'll also be able to download these slides from the resources section below and rewatch the lecture from this page. So if you want to come back over and have a look at anything, you'll be more than able to. And there also is a live Q&A off to the side or down below, so make sure you ask any questions you have in there as we go along, and I'll be available to answer those. So thank you again for joining us, and let's get into it. So we're going to be starting with bivariate data. So briefly to review, what is bivariate data? Well, if we break it down, bi is meaning 2. How I like to remember this, bi in bicycle, binoculars, we're always talking about 2. 2 eyes, 2 wheels, we're talking about 2. And then variate is referring to variables. So when we're looking at bivariate data, what actually is it? It's data with 2 variables. So we're going to have 2 lots of numbers that we're like measuring or recording. So examples of bivariate data, height and weight. They're 2 different variables, 2 different things that we're investigating, and then because we are looking at those 2 different things, we actually have the added bonus of, now that we're looking at 2 different variables, we can actually also look at the relationship between these variables. Whereas when we only have univariate data, which is data with 1 variable, for example, just height, we have nothing to compare it to and we can't look at any relationships. That's when we more look at like mean, median, and mode when we only have that one variable. But when we have our bivariate data, that's when we can start to look at like correlation and creating a least squares regression line and all of that. Another one is temperature and ice cream sales. Again, if we record both the temperature on a given day and the number of ice cream sales, we can start to have a look at the relationship. So for example, when it's warmer, do we sell more or less ice cream? And we can start to have a look at what that relationship might look like. So again, the buzzwords, we're looking for patterns, associations, relationships. We're always interested in how are our two variables related. And there are multiple types of bivariate data as well. The first kind of distinction I want to make as well is the difference between the explanatory variable and the response variable. This is just terminology that could also pop up on a multiple choice question, but it is also really important and valuable for some of our further things when we start to look at scatter plots and correlations and everything as well. So what is the difference between the explanatory variable? The explanatory variable may explain the associated changes in the response variable. So we're looking at correlation, we're looking at the relationship between two things, but when we're deciding which we think is the explanatory variable, that's the one we think is causing the change, and the response variable is the one that we think is the one being influenced. So for example, in my temperature and ice cream sales example, I would say that temperature would be the explanatory variable and ice cream sales would be the response variable. And if I put it into this sentence format, that helps it make like a little bit more sense. So like the variation in temperature may explain the associated changes in ice cream sales. So the changing temperature is what I think is causing the difference in my ice cream sales, which makes sense because on really hot days, you'd expect more people to be wanting to buy ice cream. The next is categorical variables. So when we think categorical variables, we're thinking categories: small, medium, large, yellow, blue. These are all categories, data that fits into different categories. Whereas on the other hand, we have numerical variables as well, which are any variables that give us like number results. So 1.7, 2, 26, 60,000, it could be anything. So a further way that we like class or kind of are able to identify numerical variables is by the fact that we normally like measure or record them. So for example, measuring height with a tape measure, like we measure it. So we know that it's going to be a numerical variable. Or if we're thinking about the number of trees in a forest, like we have to count it. So we know that again, it's going to be like that numerical variable. So, question, is the age of a car or the price of a car the response variable? You can have a think about that one. And our second one is height measured in centimeters a numerical or a categorical variable? So for the first question, I would definitely say price. Because again, when we think about what's the difference between an explanatory variable and a response variable, the explanatory variable is the one we think is driving the change, which here I think the age of the car would be what's affecting the price, and the response variable, kind of like the outcome, is the price. So if a car is older, that's going to probably cause it to be a bit cheaper. And if a car is a bit newer, that's probably going to be associated with a slightly like higher price because it's a newer car. And our second one, I would definitely say numerical, because we're measuring height in centimeters. So that's something we're having to like measure and count, so it's numerical. Another little difference there that I like to keep in mind is the idea that numerical data is often like continuous. So it can go on and on and on, like it might have decimals, it might have like countless options. But categorical data, like categorical variables, like it's a much more narrow range of like the options that we might have. So we normally have like a discrete and limited number of categories. Like, what is your favorite flavor of ice cream? And we might have like 5 options for people to choose from. So we have a discrete number of categories, which when we're thinking about the difference between numerical and categorical data, that has a lot of implications for like how we represent it and discuss it. So speaking of, the first thing that we have here is two-way frequency tables, which you may or may not be familiar with. So how a two-way frequency table works is the idea is that it goes two ways and it records the frequencies of our outcome. So we have one variable that goes this way and then one variable that goes this way. So each kind of number is representing a certain category. So here we're looking at like the explanatory variable we've said is gender, and we've said the response variable is like pet or like pet preferences. So here we're thinking that somebody's gender may explain their pet preference. And here we have some data that's been really neatly arranged in a two-way frequency table so that we can actually start to see if we think that may or may not be accurate. So we can see that out of the females we interviewed, 47 of them preferred cats, 17 preferred dogs, and out of the males in this imaginary sample, 39 preferred cats, and we had 64 males that preferred dogs. So from here, you can see we have a few blank squares in our table. So what we can actually do there is we can actually fill out the total columns. So for example, to figure out the total number of females that we interviewed, female total numbers, we'd add these together because the number of females that voted for cat and the number of females that voted for dog is going to add up to the total number. Same for males, total number of females, total number of males, and we can also calculate it across the rows. So total number of people that voted for cat and total number of people that voted for dog. So two-way frequency tables, what do we know about them? So they usually display categorical data. That's one thing I would like to draw your attention to. Don't be fooled by the numbers, 47, 17, 39, 64. Our variables are still categories. And so to illustrate that a little bit further, I'd like you to imagine if we were going to have a two-way frequency table for temperature, imagine all of the columns we would need. So if, for example, I pull up my laser again, if our explanatory variable was temperature, imagine if I had to have a column for 17.1, 17.2, all the way up to 29.1, 29.2, 29.3. I could, because numerical data is like continuous, and it's ongoing, I could literally have like almost an infinite amount of rows and categories, which just is not a helpful way to represent our data. But when we're looking at categorical data, remember that's our like discrete number of limited categories. We have like the benefit of, like I said, there's only that discrete number of limited categories. So it's actually a really nice way to represent this data. Here, for example, we only have female, male, cat, dog. We've got two variables and we only have two categorical options for each. So it's a lot easier to represent it this way. And again, while we do have numbers representing the amount of votes we had for each category, our variables themselves are gender and pet. And they're definitely categories because the categories we have in this scenario are female and male and cat and dog. And totals, like I said before, they can actually be expressed in either numbers or percentages. So what I mean by percentages is we can actually take the number and convert it to a percentage. And that actually allows us to compare like the numbers and the values on equal footing. Because at the moment, you can see that I've actually interviewed quite a lot more males than females. So it's actually not fair to say, well, 47 females prefer cats and 39 males prefer cats. So therefore, females prefer more cats. That's actually not a fair comparison because I've interviewed more males. So to remove the impact of that, we can actually calculate it as a relative percentage, and then we can compare the numbers in percentages. Because can you imagine if I'd interviewed 100 females and only 3 males, I would be able to say like, oh my goodness, like 80 females preferred cats and 0 males preferred cats. Like, look at this awesome data, but it's actually not awesome data because we haven't collected enough to be able to draw a reliable conclusion. So when we only do have these small sample sizes, or just even like varying sample sizes, to compare it on equal footing, we actually need to calculate percentages, which we're going to have a look at here. So you can see I've got our table here. Again, we've got female, cat and dog votes, male cat and dog votes, and we've got the total. So we had 86 votes for cat and we had 81 votes for dog. But again, because we've interviewed different numbers of people, we're going to calculate like the relative percentage frequency so that we can kind of compare them on more equal footing. So you can calculate percentages going across for rows. So this would be 100% here and this would be 100% here. Or you can do it for the columns, in which case it'd add up to 100% this way and 100% this way. So what you're looking for depends on what your question is asking you. So here we're doing an example of calculating it for our rows. So we're going to calculate the percentage of females who prefer cats. The awesome thing about doing the percentages is it's just regularly how we calculate percentages. So we take the part, divide it by the whole, and that'll give us a decimal, and then we times it by 100 to get the percentage. So part is the number of females who prefer cats, which is 47. And then we divide it by whole, the total number of people that prefer cats, which here we can read from our table is 86. So we divide 47 by 86 and we multiply it by 100. And that gives us 55%. So now when I'm talking about the 100% of people who prefer cats, I can say that out of these people, I can say that 55% of the people who preferred cats were female. And then if I fill out the rest of my table, I'll have a lot more data I can discuss as well. So for example, here is an example of that table all filled out. So you can see that I've got 55% of the people who prefer cats are female, and then that leaves 45% of males who prefer cats. Because again, we know it's going to add up to a total of 100. So my options are either do this calculation again, so part over whole, 39 over 86 times 100 will give me 45%, or also because I know it's going to add up to 100%, sometimes I could just go, well, 100%, take 55%. I know it must be 45% of males that prefer cats, but sometimes with rounding errors, that's not the most reliable way to do it. So I'd still definitely recommend just always calculating it from scratch where possible. And then we've done the same for dogs, calculated out of the total number of people that like dogs, what percentage of them prefer, what percentage of those people are female and what percentage of those people are male. And now that we've calculated the percentages, we can actually compare these things on equal footing. And then from there, we can actually draw conclusions and answer a whole bunch of different question types about our data. And another hint that I have for you guys is when you're writing reports about data, I actually find the teal paragraph structure really helpful. I know it might sound like a bit of an English thing, but it can just be like a mental cue to help you to remember to make sure you're including all of the information. So T, topic sentence, what's your point? Are we saying that females are more likely to prefer cats or dogs? Are we saying males are more likely? What are we actually saying? So making your point and your stance. And then evidence. The most important thing when you're asked to like draw a conclusion is to actually give evidence. And if it's talking about evidence, it's probably talking about numbers from the table or the calculations that you had to do. So I want to see numbers in your answer. I want to see 55% in comparison to 45%. I want to see like you comparing all of these different numbers, and then explain if there's any other information you feel like you need to add to communicate what you're discussing. That's really important to make sure you communicate that as well. And then like a linking sentence if you want to summarize your point. So I just find that's a really helpful like cue in my mind to help like make sure that I'm remembering to include all the appropriate things. But you don't necessarily have to follow that structure, but as long as you remember to really clearly make your point and back it up with evidence from the table. So those two things are really, really important. And make sure you're actually answering the question. So you're not just summarizing the table, unless that's what you've been asked to do. You'll probably be asked to draw a specific conclusion about your two variables. So make sure you're always reading the question really carefully as well. So our two-way frequency tables, that's how we represent and make sense of our categorical data. So our discrete categories. So for example, the one we just looked at was like pets and gender. We only have a few discrete categories in each, so it made sense to represent it in a table. But this example here is an example of a scatter plot. which you might have looked at in class already. So scatter plots represent bivariate numerical data. So when we have two numerical variables, scatter plots are really awesome. Obviously, they represent this really well. Because again, coming back to my analogy like with a table, can you imagine if I had to have like a column or a row in my table for like 20,000 kilometers, for 35,000 kilometers, for 49,000 kilometers, for 161 and 743,000 kilometers. It just doesn't make any sense. It's not practical to represent this in a table. But that's where scatter plots come in super, super handy for representing bivariate numerical data, because it is ongoing, it's continuous, there's so many different possible variables. But by having this one axis with all of the numbers along it, we can actually plot every point. And every point has a corresponding value for our explanatory variable, which is along our x-axis, and our response variable, which is along our y-axis. So this car, for example, has driven about 265,000 kilometers, and it costs about $9,000 approximately. If I was going to check exactly, I could, but just by having this scatter plot, we can actually read off it and get a lot of information about it. So like I said, another really good thing about scatter plots is they're visual. We can see patterns, we can see trends, and then we can actually observe them and discuss them and see what do they actually mean. A few key things in scatter plots: make sure title is always really important. And again, we're usually talking about correlation in scatter plots. So I've called this correlation between kilometers traveled and price of 2012 Toyota Corollas. And it's just fairly standard form as well, that you put your explanatory variable on the axis down the bottom, and the response variable goes on your vertical axis, your y-axis. So here, kilometers traveled, I thought that was my explanatory variable, because I thought how many kilometers the car has traveled may explain like the change in the price of the car. Definitely not the only factor, but I definitely thought it might be a big factor. So this is how I put together my scatter plot. And you can start to see that we actually do have like a pattern. Patterns are just any overarching trends or any conclusion you can actually draw from your scatter plot. And so that's, a quick introduction to scatter plots. So there are lots and lots of different things we can actually talk about when we're discussing a scatter plot. The first thing we can talk about, is it a positive direction? Is it a negative direction? Or is there no association? All right, I don't know if I have a slide for that, but let's discuss what that means now. So direction, is it positive? Is it negative? Or is there no association? So what I'm seeing here is a overall decreasing direction. That's the trend that I'm seeing. So this scatter plot, I would say, has a negative direction. If it was going to have a positive direction, it would mean it would be moving up. So as one variable increases, the other one would be moving up. But that's actually not what we see here. We actually see that decreasing trend, which is our negative relationship. Of course, the other option is no association. So that's if our points were all kind of just randomly scattered about and there's not really any sense of direction to it. We'd say it has no association, because you can't have a positive or negative direction in that scenario. But here we have a negative direction. So we can see that that's telling me that as the kilometers traveled increases, the price of the car decreases. So that's what our negative relationship is. As one variable increases, the other variable decreases. Whereas in a positive relationship, as one increases, so does the other. And that's how we get that positive relationship. So again, whenever you're discussing a scatter plot, we're thinking direction, form, strength, and outliers. So direction, I've decided it's negative. Form, linear or non-linear. So linear is saying like it's forming like a linear pattern, like a straight line. Whereas non-linear, it could be like going like this, or it could be like changing directions, anything that's not in a straight line. This does appear to me to be a linear pattern, because it does look like it's following a straight line for the most part of things. But there's some further statistical analysis, like a residual plot, that tells you a little bit more about that, and we'll get into that soon. So I'm going to say this is linear for now, until I can see if it is by testing that out later. Strength, is it weak? Is it moderate? Is it strong? This is looking fairly strong, so I'd probably say like moderate to strong, because if it was weak, the points would be quite spread out. If it was strong, they'd be really close together. So, but there is definitely a fairly strong looking pattern there. So I'd say it's like a moderate to strong relationship. And I don't really see like any obvious outliers. Like, I mean, maybe that one, but not really. It still like generally falls in with our pattern. So if I was going to describe this, like I have on our next slide, I would say the scatter plot revealed, like I did say a moderate to strong. I said it was negative, and I said it was a linear association with no evident outliers. So when you're discussing the relationship between two variables, those are all of the key things that you want to be hitting on. But let's get a little bit more specific. I just estimated the strength of that scatter plot. I said it was like moderate to strong. That is incredibly vague, and it's only an estimate. So it's not a very specific way to discuss the strength of a correlation, which is where the correlation coefficient comes in. The correlation coefficient is an R value, which tells us the exact, precise mathematical strength of the relationship between these variables. And it's a very long process to calculate it by hand, which we won't be going through in this video, but it is something you'll definitely be covering in class. And yeah, it's very important to be familiar with that process. So what does an R value tell us? R values tell us the strength of a linear relationship, and they can range between -1 and 1. So -1 is a perfect negative relationship. So if we had like a little scatter plot here, a perfect negative correlation would be like a direct perfect negative correlation. And +1 would be a direct perfect positive correlation. If it's close to 0 in the middle, that means like all of our dots are like really randomly scattered around and we don't really have an association present. But you can start to see how like having this range and like the statistical process of calculating an R value, that's actually a really valuable thing, because it can tell us the exact and precise mathematical strength of the relationship. But one thing I will show you is how to calculate this with a calculator. This is one of the most time-saving and helpful tricks I know. It certainly doesn't replace actually knowing the full process and how to calculate it, because there is a chance you'll need to apply that within an exam, for example. But if you're asked to calculate a correlation coefficient, for example, like a multiple choice question, or if you wanted to check your answer, being able to kind of do that on a calculator is such like a massive like time saver, and it's just like a very valuable trick to have in the back of your mind. But again, it doesn't substitute knowing the actual process. And my last hint before we get onto that is to be really familiar with your formula sheet, which I've linked in the slides, so you can go down and download those as well if you'd like to, because it's really, I can't stress enough how important it is to know what's on your formula sheet. It is a publicly available document. You're meant to be able to be familiar with it. And why it's like so important is so that you know what formulas are on there, and so that you know how to use the version that's on the formula sheet. Or if you don't like the specific version on the formula sheet, you'll know that you need to memorize the one that you prefer to use, so that you'll have that ready in your mind to use in the exam. And also, not all the formulas are on the formula sheet. So being very familiar of what's on there, do you know how to use it, and is that the version you want to be using? So get familiar with your formula sheet as well as the syllabus. They are like the most handy documents, because they pretty much tell you, they're designed to tell you what you need to know and how to approach it. So definitely find those ones. So this here, again, slides available to download. I definitely recommend you taking a photo or downloading the slides or jotting this down or giving it a try now on your calculator so you can have a practice of it. But yeah, this is how to calculate a correlation coefficient using your scientific calculator. So if you press mode, which should be a button on my calculator, it's in like the top right hand corner. If you press mode, it'll pop up with 3 options. What you want to do is press 2 for the stat mode, which will put your calculator into statistics mode, which changes it in some small way and is just part of the process of how you get to where you want to be, I suppose. And then you press 2, which will say a plus bx, which is referring to the fact that it's bivariate data. And then what you do is a little table will pop up and you enter your X and your Y values. So you might move around the grid using the arrows. You might go like, up and down, left and right, and you enter the number and then click enter. And then you enter your next number, click enter. Then you might need to use the arrows to move around to like the Y column, for example, until all of your X and Y values are entered. So you'll have a corresponding X and a corresponding Y value for each value. And then you press on, and this will clear your data, but don't stress. It's all part of the process, and the calculator does have it stored in its memory. The next few steps, you kind of do need to remember these ones a little bit as well. You press shift, and then you press 1, and then you press 5. And it'll come up, the option for 5 will say reg, and that's short for regression. And we're doing regression analysis. So that's the type of data analysis that we're doing. And then the option for 3 will be R, which is the correlation coefficient. So then you press 3 for R and then equals, and it will give you a correlation coefficient. If these little prompts don't pop up, you might have done something a little bit wrong along the way, so you might need to try that again potentially. But then as long as it gives you a number, and it should definitely be between -1 and 1, you'll know that that's giving you the correlation coefficient. So this massive time saver, I definitely recommend you learn this process, because for general maths, we get our calculators for both exams, which is just so beyond valuable and helpful. So definitely make the most of that. And then my last little tip is make sure you put your calculator back to the regular mode once you're done, just because the statistics mode can really mess with the settings a little bit. I don't exactly know how it works, but it is important to put it back into the regular mode. So you press mode again and then 1, which will say comp, and then to switch it back to the normal mode. And then if you need to do any more statistics calculations, you just again go back to the start, press mode 2, and it'll be back into statistics mode. So definitely take note of this. It's incredibly helpful. And again, if you have any issues with that, please let me know in the live chat and I'll be there available to help you out with that. And hopefully, get you on the right track with that, because it's a really, really helpful trick. Awesome. This is another really valuable resource. This is like a rough guide for how to interpret R values. So again, anything above 0 is going to be positive. The number is positive, means it's going to be a positive correlation, which reflected on a scatter plot means it's going to be moving up. Because again, positive means as this variable is increasing, this variable is increasing too. So that's positive. And the stronger it is, the more predictable the relationship is, the more strongly correlated they are. And again, anything below 0 is going to be negative. And again, as we get closer to -1, it's going to be stronger negative, and as we get closer to 0, there's a weaker association or no association if it's around 0. So again, this is just a rough guide or chart of how to interpret R values, and then also what that looks like in a scatter plot, so you can kind of visually get an idea of what that looks like. And that brings us to a least squares regression line, which is kind of the next step in a regression analysis. So if you've heard of a line of best fit, you've kind of heard of a least squares regression line. So a least squares regression line is a mathematically precise line of best fit. So in a test before, especially when you were younger, you might have been asked to draw a line of best fit. You might have just taken a ruler or even just your pencil and just drawn a line through it, that estimated and roughly represented the overall trend. That's an awesome thing, but it's not mathematically precise. So the process of calculating a least squares regression line is how we get that to be more precise. And the formula of the structure of how we do that is y equals bx plus a, where y is our response variable, which we've discussed. B is the slope or the gradient. So this can be a little bit trickier to interpret. So the gradient, or B, estimates the average change in y, which is the response variable, for each 1 unit increase in the explanatory variable, which is x. And then A is the y-intercept, which is where the trend line or the line of best fit intercepts the y-axis. And the cool thing about that is that's always going to be when x is equal to 0. So that's kind of how you go about finding the y-intercept, because when x is equal to 0, So if, for example, I draw us a scatter plot example here, if, for example, our line of best fit looked like this, we can see that this here is where my line intercepts the y-axis. And that's really valuable to note because, well, first of all, because it's a part of our equation, but also because it tells us more about like our data. So we know that this point here is where it intersects. This is our this is our y-axis. So this is where our line intercepts our y-axis. Conveniently though, this is our x-axis, whatever our scale is, might be 0, 1, 2, 3, 4, 5. Where the line intercepts the y-axis, it's always going to be when x is equal to 0. So that's another cool little trick as well, if you're ever needing to calculate that. And then coming back to like the slope and the gradient, so that estimates the average change in the response variable for each 1 unit increase in the explanatory variable, or like the x in the case of the formula. So here, for every 1 unit increase, we have in the x, which is again explanatory variable plotted along this axis, what's happening to our response variable. So in this one, we can see that with each 1 unit increase, our response variable is also increasing. So here you can see we're going to have a positive slope or gradient. It's going to slowly increase because for every increase we have in x, we also see an increase in y. Whereas, for example, if I had a negative line, for every increase in x, we're going to have a decrease in y. Increase, we're going to decrease, decrease, decrease. So it depends what type of like trend, pattern, relationship that we're looking at. But that is a quick overview of how to interpret the least squares regression line. So here you can see I've got an example. You can see that I've got y, so my response variable, which here is the price of the car. So here I'm saying the price of the car is equal to negative 0.0406 multiplied by the kilometers traveled plus 17,643. So you can see if my line was to continue up and intercept the y-axis, and you can also see x is equal to 0, the value that's going to be there is about 17,643. So that's using my line to predict what the price of a car is when x is equal to 0. So when it's traveled 0 kilometers, this line's predicting the price of a new car. But again, extrapolation isn't always super reliable for a lot of reasons, which we're going to touch on a little bit later. And then we can also see that for every 1 unit increase, so for every extra kilometer the car travels, the price of the car is dropping by about 4 cents. So that's how I'd interpret this here. Or that could be 0.04 cents. It depends on the unit we've used. Probably 4 cents, I think, if I am interpreting that correctly. But again, it's negative. So for every 1 unit increase, my response variable is dropping. So for every kilometer the car travels, it drops in value. The price of it drops, which makes sense because that's the kind of relationship that we're looking at. So again, calculating A and B by hand, bit of a time-consuming and painful process, but also really important. But you can also calculate this using your calculator. But again, it's not a substitute for knowing how to use the formulas in your formula sheet, because that's a really important part and could definitely be assessed on your exam as well. So similar process, mode 2 puts it into statistics mode. Then you press 2, which again is to get up that bivariate data table. You enter your values. Again, you press on. You press shift 1, 5. Again, same process as before to get into like regression, I believe. And then you can choose. 1 will give you the value for A, and 2 will give you the value for B. And then you can go back and do the process again if you want to find the other value. So you can also use your calculator to find A and B. Again, really helpful information to tuck away in the back of your mind. Another thing I'd love to touch on is the difference between like association and causation. The biggest and the most important takeaway from here is that correlation does not imply causation. So for example, if some random study found a massive correlation between divorce rates and margarine consumption, should we conclude that consuming margarine causes divorce? No, like that's a completely illogical conclusion. There are actually multiple non-causal explanations for an association. And the other thing to consider as well is if it was a really small sample size, like it might actually just be like a fluke, which is actually one of the explanations we're going to look at as well. So the first one, common response, when two variables are strongly associated because they are both strongly associated with a third common lurking variable. So this is where general maths isn't black and white using formulas. It's actually, you've got to do like a bit of like thinking, which is why I find it quite interesting. So for example, scenario, if a study found a really strong association between like the number of scarves worn and the number of hot chocolates sold. Does that mean the number of scarves worn and the number of hot chocolates sold are like directly correlated? Well, no, it actually doesn't. There could be a third like lurking common response variable, such as the temperature. So in this scenario, the temperature is associated with the number of scarves worn, and the temperature is associated with the number of hot chocolates being sold, because if it's colder, people will wear more scarves and buy more hot chocolates, which has made it seem like scarves and hot chocolates are correlated, but they're actually not. It's actually that lurking variable. Another one, confounding variables, where there are actually two possible causal explanations. An interesting example of this is crime and unemployment. When we look at that sociologically, does crime drive people to unemployment, or does unemployment drive people to crime? Interesting. Which way does it go? How can we know? Another really interesting thing is when we're only doing like observational studies or correlational studies, when we're just like observing and collecting data, we can never actually talk about causation. We can only talk about correlation and association. To be able to talk about like causation, you have to conduct an experiment, which is where you like directly choose to manipulate a variable, which is something you might have looked at in science before. But we're only looking at association and correlation, so we can't be talking about causation. And like we touched on before, it could also just be a coincidence. Maybe their sample size was too small. Maybe the specific sample they looked at had this like correlation going on, but maybe it doesn't hold true for everywhere. Like it's just, sometimes it is actually just a coincidence. So that brings us to topic 2. Good work, everyone. We're doing well, getting through some of the content, which is awesome. If you're still tuning in, thanks so much. And again, feel free to pop any questions you have in the live chat as we're going along. But yes, we are up to topic 2, which is awesome. Time series data. It is a whole new topic, but the awesome news is that a lot of it is actually quite similar to topic 1, bivariate data, because time series data is still bivariate data. It's just a special kind of bivariate data. And the kind of like the defining thing for time series data is that it's bivariate data where the explanatory variable is always some measure of time. So what happens is a variable, our second variable, the response variable, is recorded at successive time intervals. And then we can graph that on a time series plot and look at how it changes over time. So we could look at temperature over the week. We could look at TV sales over the week. We could look at temperature over the year. There's all of these different things that we could look at and how they change over time. So again, with bivariate data, our EV and our RV, our explanatory variable and our response variable could be like a massive number of different things. And here our response variable can still be like anything that we're looking at, but the kind of like the different thing is it must be looking at how it changes over time. So our explanatory variable must always be some measure of time, how something changes over seconds, minutes, weeks, months, years, decades, any measure of time. We're always interested in how our response variable is changing. So for example, temperature and ice cream sales. This actually is not an example of time series data because we don't have an explanatory variable that's a measure of time. But If we looked at ice cream sales, like the average monthly ice cream sales over the year, then all of a sudden it is time series data because we're looking at how ice cream sales change over time. And then we're looking again at those patterns, relationships, associations. So we're thinking about like, oh, that's so interesting. We're selling a lot more ice creams in December and we're not selling a whole lot in July. Why might that be? It's related to temperature most likely. But again, it's got to have some measure of time for it to be time series data. And we'll have a look at an example just in a second, but another thing I want to flag is that we do connect the dots in a time series plot because time represents a continual, precise, linear, and unchanging relationship. Whereas when we had our bivariate numerical data scatter plots, we just had heaps and heaps and heaps of points everywhere, so it made like no sense to connect the dots. But with time series data, we normally just have a 1 point at each time interval. And again, that's like precise, that's a continual, linear, and unchanging relationship. So we can connect the dots, like in the example we have here. So this look, again, time series plots, very similar to scatter plots. We're still graphing bivariate numerical data, but again, our explanatory variable, which is always graphed down the bottom, must always be some measure of time. And here, that's by months. So January, February, all the way through all of the months. And what we're looking here, this is actually a specific example of seasonality, which we'll get to in a second. But what this time series plot is about, it's about the mean or like the average temperature per month. So our response variable, which is graphed on the y-axis or the vertical axis, is temperature. So here we're interested is how does temperature change over time? That's what we're looking at. And interestingly, we can see the temperature is higher, like around January. It's lower around July, and it's higher around December. That makes total sense because of like the seasons that we have here in Australia. So you can start to see this, like how our time series plots are really, really helpful for representing that time series data. So again, it works the exact same as a scatter plot in how we plot the points. Every point represents like a time element on the x-axis, and then the response variable will be plotted on the y-axis, and so the dots will all represent that. And again, the main difference with a scatter plot is we normally just have like one dot like per time point, and then we can connect them because of that continual, precise, and unchanging linear relationship. And so when we're actually discussing time series plots, when we were discussing scatter plots, we talked about the nature, the direction, the strength, the form, the outliers. That was the language we were using. But we kind of switch gears a little bit when we're talking about time series plots. There's slightly different like language and features and patterns that we actually look at. And the syllabus tells us what kind of terminology we're going to be using. And again, you can download these slides from the resources tab if you did want to use that link to go to the syllabus. So we can see here that topic 2 of unit 3 about time series analysis is about describing and interpreting patterns in time series data. So this is something that you need to be able to do. So first bit, you need to be able to actually construct time series plots. So again, we went over briefly some of the key features. You need title, axis titles, units, the dots, connect the lines. That's all of the main things for time series plots. And then this next dot point is saying you need to be able to describe time series plots. And this tells us what kind of language they're going to be looking for by identifying features such as trend, which is like a long-term direction, so a long-term increasing or decreasing trend. Seasonality, which is like systematic calendar-related movements. We're going to define all these in a little bit more detail shortly. Irregular fluctuations, which is unsystematic short-term fluctuations, and recognized outliers, which are once-off unanticipated events. So, trends. Again, like what the syllabus said, that's like the overall tendencies for values to increase or decrease over a period of time. So here we have an example of an upward trend, which is reflected by this trend line here. And then here we have an example of a downward trend, because we can see that over time, so as time passes or as time increases, our response variable is decreasing. So that's when we're getting a downward trend, like that negative relationship. But here's a positive trend because as time is passing, our relationship is going up. The third one I'll draw your attention to is the fact that we can also have mixed trends. So it might go up for a time period, down steeply for a time period, and then level out by a time period. And you can also reflect that using multiple trend lines. So that's something to keep in mind as well. So again, that's what a trend is. And we can use trend lines to identify them, like we've done in these examples here. The next one, seasonality, same graph that we were looking at a little bit earlier. So seasonality is kind of any patterns that we see with calendar-related periods or calendar-related patterns. So if there's like a weekly pattern, a daily pattern, or a seasonal pattern, like that's all what we're looking at. So patterns are often, these kind of patterns with seasonality are often quite predictable. And again, if we're discussing a time series plot, teal is actually a really good structure to come back to because T, we're thinking about like our topic sentence. What is it that we're discussing? What have we noticed? E is evidence. Whenever you're like kind of maybe giving a bit of a paragraph answer on like describing what you're seeing, describing like what you're seeing in your like time series plot, it's important, really important to make sure that you're actually giving evidence, and the evidence that you need to give is like the numbers and the patterns and the trends that you're seeing in your time series plot or like your time series graph. Like, you know, for example, I'm seeing like like that low point around month 6. Like those are all the type of things that you're going to be talking about. So seasonality is all about those patterns that are like related to the calendar. So here we're definitely seeing like a very because we're looking at like the mean temperature per month. So we're definitely seeing seasonality here because we're seeing a pattern that's really like related to like the months or like the seasons, which you describe that as like a quarterly pattern because the seasons are about the 4 quarters of the year. And seasonality is often quite predictable. Because on the other hand, when we have cycles, they're very similar, but there are some key differences. So cycles, like we said, they're like seasonality, but the main difference, which is really important to keep in mind, is that with cycles, again, predictable patterns, but the period is usually a year or greater, and they're usually less predictable than seasonality. So with cycles, we're actually looking at really long-term trends and patterns. So this could be like, this could be months or this could be years passing. So we're looking at really long-term repeating patterns and trends. And again, they're usually a bit less predictable than seasonality. So yeah, that's really important to keep in mind the difference between seasonality and our cycles. The next thing important to be able to discuss is structural change. So structural change is where we see like a significant change in the established pattern that was previously consistent in our time series plot. And it often does result in a new trend. And it's often like caused or reflected by like significant like external events. Like if like the economy crashes, or if there is a war, or if there is like a snowstorm, like that's all gonna have a serious impact on if we're looking at like temperature data or financial data. So you can see here in this example, we have like this really strong, like steep increasing, like positive increasing trend and pattern. And then we actually have a structural change around time 13. So again, it could be months, days, weeks. This example doesn't specify. You can see that's actually resulted in like a new trend or pattern. It's kind of like it does decrease a bit and then increase a bit, but it's fairly level compared to our previous pattern. So structural change, again, it's like that significant change in a pattern that was previously consistent, and it normally does like have an external cause. The interesting different thing is outliers. So what's the difference between outliers and structural change? So outliers are a single unexplainable point that stands out from the rest of the data. Whereas you might have noticed that when we had our structural change, there was that big change and then it continued with a new pattern. However, here with our outlier, we have a single unexplainable point that stands out from the rest of your data. So this is going to be really important to take into consideration when we are discussing like our time series plots, because that is a factor that's like very heavily influencing it's very much influencing our data, and it's something to be able to discuss when we're just looking at like patterns and what we see. Next is irregular fluctuations, which is essentially everything else. So all things unpredictable and unexplainable that don't fall into the previous categories. The reality is that in any real world data, we're going to have irregular fluctuations, like the random up and down. That's not this beautiful, predictable and smooth patterns, because irregular fluctuations, those random changes, are going to happen in temperature, in sales, in almost all of the data that we look at. So that's something to keep in mind as well. However, sometimes we do not want the irregular fluctuations to skew our data. Sometimes these irregular fluctuations can actually like obscure underlying trends. So we might think like, oh, there could actually be an underlying trend here, but it's just so obscured by all of these irregular fluctuations, like I actually don't know. So that's where the concept of smoothing comes in. So smoothing is like a concept or like a technique that's actually the goal of smoothing is to remove the impact of those irregular fluctuations. So for example, like in that data we had before that had all of those random irregular fluctuations, the goal of smoothing is to kind of try and iron out those effects. It's like, hey, we actually really want to remove the impact of these irregular fluctuations so that I can actually see if there is any underlying trends or patterns. And there are 4 types of smoothing. So again, smoothing is a technique to overcome variation. Not so much seasonality, because we'll look at like deseasonalizing and reseasonalizing data shortly, but mainly irregular fluctuations. And again, it's about trying to uncover those underlying trends. So the 4 types are the 3 moving average and like the 5 moving average, or you might have heard it referred to as the 3 moving mean and the 5 moving mean. And we're going to have a quick look at those 2 today. There's also 2 other types. There is the 2 moving mean with centering and the 4 moving mean with centering. And I'll explain those shortly, but we won't really go into those 2 as much in today's video. But the idea of the name behind them as well, how they get the name, which will remind you how to apply the formula, is actually how many points that we're using to smooth each point. So to illustrate that a bit further, in the 3 moving average or the 3 moving mean, which is a type of smoothing, what we do is we take each value or each data point and we average it. So we take each value and we average it with the point to the left and the point to the right. So we're finding the average of 3 values. And because we take the point to the left and the point to the right, we actually can't smooth the first point and the last point, because there's no point to the left of the first point and there's no point to the right of the last point. So we do lose our first point and our last point, but we are able to smooth all the values in the middle. So to illustrate the 3 moving average, here we have some time series data. I can see that because our explanatory variable is time, and then our response variable in this specific scenario is the number of houses sold. So in January, 12 were sold, February 8, March 7, but potentially maybe they've graphed this data and gone, oh, I think there might be some irregular fluctuations in here. So what we're going to do is we're going to use smoothing, in this case the 3 moving average or the 3 moving mean, to try and overcome this. So again, step 1, we cannot smooth the first month because there's no point before it or no point to the left of it to smooth it with. There's no month before January in this data set. So we have nothing to average January with. So we can't do January. So we move on to February. So to get the 3 mean or the 3 mean smoothed point for February, like we said before, we take the point for February which is 8, and the point to the left, or the point before, and the point to the right, or the point after. So to get the averaged point for February, we're averaging the values for January, February, and March, which is 12, 8, and 7. You've got to add all of those together, divide them by 3, which gives us 27 divided by 3, which is 9, which gives us our 3 mean smoothed value for February. And so you can kind of start to see how like the process of smoothing plays out. By doing all of this averaging, we're kind of trying to like remove the impacts of the irregular fluctuations. I think we have a graph coming up shortly that might help illustrate that as well. So next, I want to find the 3 mean smoothed value for March. So I'm going to take the values, the original values, not the smoothed values. We do all of our calculations with the original values of February, March, and April. 8, 7, and 14, and we add them all together, divide them by 3, again, the process of averaging, and that gives us our value for March. And then you go through and do the same thing to get the 3 mean smoothed value for April. We take the values for March, April, and May, average them, and that gives us kind of like a smoothed value. So that's kind of how our process is working there. Very, very similar process with our 5 moving average. So how that works, same thing, except we're using 5 points. So we're taking the point, that's our point of interest, and the 2 points prior and the 2 points following. So we're using 5 points. So that also means we can't use January, but it also means we can't use February. And if we went all the way to the end of this year's data, we also couldn't use November and December, because there's no 2 points after November and December. Same with our 3 moving average, except we just wouldn't be able to use December because we could average November, but then we couldn't do it for December. So 5 moving average, same deal. I'm taking the point for March and the 2 points beforehand and the 2 points after. I'm adding them together, I'm dividing them by 5, and that gives me my value for March. And then that's the process of it. So here we can really start to see what the effects of it is. So let's break down this a little bit more. So this is our data. Houses sold by month. Before we had it in a table, now we have it in a time series plot. It's visual, it helps us to see it. So the color coding is a little bit hard to see, but we can see here that our original, and we can also tell our original data point because it's got all 12, and we can tell this is our 3 mean smoothing because we're just missing the first and the last. And we can tell this is our 5 point because we're missing the first and the last 2. But coming back to our original, we can see really clearly now that it's been visually graphed, all of these are regular fluctuations. Like there's not really much of a pattern going on. And when we have our 3 point, we've got to follow it kind of carefully. We can see this is our 3 point. You can kind of start to actually see that our data is in fact being smoothed. It's kind of being flattened. Like the really up and down rough irregular spikes, like it's actually kind of being smoothed and ironed out. Like you can actually see that process happening. And then when we come to our 5 point, and again, the more points you use, the more it'll smooth it out. Our 5 points, we can see it's even more smoothed. And now that we've done all of this smoothing, we can actually kind of start to see a tiny, tiny little bit of a potentially an increasing trend. Not a whole lot, but maybe a tiny bit. But that's just mainly to get you thinking in the groove of, okay, well, now that I've done my smoothing, we're going to look again for those trends and patterns. Is there now an increasing or decreasing trend that I couldn't see before because it was obscured by those like irregular fluctuations? But just to quickly illustrate the 2 and 4 moving mean with a centering for you, I'd just like you to consider for a moment, what if we took the average of January and February? Because, you know, if 3 moving average uses 3 points, 5 moving uses 5 points, 2 moving uses 2 points. Yep, that's awesome. That's a correct train of thinking. But if we take the 12 and the 8, we add them together, we get 20, we divide them by 2 because that's how many points we used, and we get 10. But 10 is going to lie halfway between January and February. So now we have this issue where we have this halfway between point where it's like halfway between January and February, and it's actually not on an original data point, which is what we want to see. So where centering comes in, gets a little bit more complicated, but what we do is we say, okay, if I take the average for these 2 months, perfect, average them out, get a halfway between average, and then if I take the average for these 2 months, add them together, divide by 2, get an average for the halfway in between, I now have 2 halfway in between averages. I have my value for here, and which is 10, and my value for here, which is 7.5. And then the idea of centering is how we get it back to the center. So I've got these 2 in between points now, but to get the centered, the 2 mean smooth centered point for February, I'm going to average this halfway in between value with this halfway in between value. And then that's going to get us a point. So I'm going to average 10 and 7.5. And then that value answer is going to be our 2 mean smoothed value with centering. So there's kind of, and then you do the same with 4 mean, except it's kind of like you got to like move it over a little bit more complicated. We won't be going through an example of that now, but it is the same process of I'm going to average the ones slightly to the left, average the ones slightly to the right, and then I'm going to average the averages to get back to the center. So you can kind of see how that's a little bit more of a complicated process. But that's like, yeah, kind of like the overview of it. And again, if you would like anything clarified, please feel free to ask in the chat. So awesome, that's our time series analysis, which brings us to seasonal indices. So first thing I want to clarify is, what is a season? Well, summer, autumn, winter, spring might be like our first thought, and that's like totally an okay thing to jump to. That's definitely where my brain goes as well. And they are seasons, but they're not the only things that are seasons. So seasons are any breakdown of time with equal periods in the year. So a season could be days, a season could be weeks, a season could be months, a season could be quarters, which is kind of what we understand seasons to be for the most part. But it's not necessarily just limited to that. So if we could have like a season for each day of the week, like, you know, we might be looking at Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, that is still a breakdown of time with equal time periods in the year. So just how we looked at smoothing before, as smoothing is this technique to overcome the effects of irregular fluctuations, kind of remove the impact of that, see if there's any underlying trends. Now we're getting into something a little bit different. What if we wanted to remove the impact of seasonality? Potentially is what we're going to do here. So seasonality, again, that might be like, you know, the temperature of various months throughout the year. That might be like sales on each day of the week. If we notice seasonality occurring, which is again those patterns within those like calendar related time periods, same thing that we're talking about here. What if we wanted to actually remove the impact of that seasonal, like remove the impact of the seasonality? That's what we're talking about here. So we can de-seasonalize data to remove the impact of season. We can re-seasonalize data, so getting it back to its original form. And how we do that is using seasonal indices. So seasonal indices scale information to reveal trends without the influence of seasons. So just like smoothing removes the impact of irregular fluctuations, seasonal indices like scale our information to reveal trends without the influence of seasons. My favorite example to kind of illustrate this is, are we selling more ice creams just because it's summer? Or if I removed the impact of it being summer or winter, is our business still doing well in spite of that? So if I remove the impact of seasonality on my ice cream sales, what trend am I left with? Are my sales actually increasing or decreasing overall? Well, we need to remove the impact of seasonality to kind of see that a bit clearer. So what are seasonal indexes? Seasonal indexes are a number representing the percentage above or below average that a particular season is. And it tells us how a particular season compares to the average season. And the average season is always 1. So the sum of your seasonal indices will always equal the number of seasons that you have. So for example, if we're looking at quarters, so summer, autumn, winter, spring, we will be looking at our seasonal indices should add up to 4 because the average of the season is 1. So it's going to add up to 4. Whereas if we're looking at months, our seasonal indices will add up to 12 because we have 12. But if that doesn't make sense yet, that's okay. We're going to go into that in a bit more depth now. So how do you interpret seasonal indices? So a seasonal index of 1.3 means that the season is 30% above average. So if, for example, our summer ice cream sales seasonal index was 1.3, that means our summer ice cream sales are 30% above the average season. And say our winter ice cream sales might be 0.5, which means that it's 50% below the average season. Because mathematically, the average season is always represented by the number 1. And then when we're interpreting seasonal indices, we always interpret it in relation to the average. So again, for example, a seasonal index of 1.3, that's 30% above average. Average is 1. 1 is representing 100%. And like I said before, the sum of the seasonal indices will always equal the number of seasons. So with my ice cream example before, my seasonal index for summer might be 1.3 and winter might be like 0.5. And then, my other 2 seasons might be a bit higher or lower. And, some of them are going to be below 1, some of them are going to be above 1. But on average, it's still going to add up to 4 because that's just like mathematically how seasonal indices work. Because if the average is 1, then it makes sense that the sum of all of them is going to equal the number of seasons because, again, averages. So we're going to go through a quick example to illustrate that. And this question is taken from one of the NEEP QCE General Maths trial exams, which are available on 8R Notes Plus. They're super helpful if you're wanting to get in a few more like practice questions as well. But this specific question here that we're looking at says, the table below shows the number of houses sold by a real estate company in each quarter of 2018. So we know we're looking at quarters. So summer, autumn, winter, and spring. Again, time series data because our explanatory variable is the quarter, like the measure of time, and then the houses sold is our response variable. So we're being asked to determine the seasonal index for autumn. So first thing I'm noticing, autumn has sold 2,837 houses. So awesome, that's quite a lot of houses. But when we look at summer and spring are both in the 3,000s, but winter's also about 2,600. So interesting. Is my seasonal index going to be slightly above or slightly below 1? I'm not sure yet. We're going to have to calculate it to work it out because we've kind of got these 2 that are a bit higher and these 2 that are a bit lower. So my thinking is that summer and spring will have a seasonal index above 1 and autumn and winter will probably have a seasonal index of below 1. So I'm thinking it's going to be A or B. And then D is just like completely wrong because that to me looks like the average of all of the numbers, but we don't want that. We want the seasonal index. That's what we've been asked to find, which we know is going to be a number around 1. So I'm already thinking it's going to be A or B. So how do you calculate the seasonal index? To calculate a seasonal index, you take the value for that season and you divide it by the seasonal average. So we'll break down that a little bit further now. So again, our seasonal index, this is our formula, is equal to the value for that season, which in our case, the value for the season of autumn, divided by the seasonal average, which is the average of all of our other seasons. So the first thing we need to do is find our seasonal average. So we're adding up the value for summer, the value for autumn, winter, and spring. Adding it up, dividing it by 4, and we've got 3,220.25. So that's our seasonal average, the average of all of our seasons, which ironically, they've tried to trick you there with D. That was what I was suspicious they were doing. So now that we've got our seasonal average, we can use our formula. So our seasonal index is equal to our quarterly value divided by our yearly average. You can see here, we've substituted into our formula. Our quarterly value is this here, which we've got here, and then divided by our seasonal average is this here. So that gives us 0.881, which is our answer for B. So our guesses were in fact correct. And we rounded to 3 decimal places because that's what all of the options were. So it made the most sense. But to conceptually kind of illustrate it a little bit further, this does make sense in my mind at least, and it's okay if you're still like kind of grasping it in your mind, because again, this is a Head Start lecture. It's just an introduction. We are going through this quite quickly, so it's okay if you do still have some questions about this. And again, that's what the live chat box is for too. So we have this number here. So the value for autumn, and this here is the average of all of the seasons. So I can already see that the value for autumn, I know that it's lower than the seasonal average. So I'm already kind of starting to figure out that I know my seasonal index is going to be below 1, because I can already see that my value for the season, it is lower than the seasonal average. So I know that it's going to be lower than 1, which is what we have here. And then, so that's the process that we've done there. And then to interpret that, or just to round a little bit to make things easier, so our seasonal index is roughly 0.88. Interpreting that based off the information that we've been looking at before, I can now say, having done this, that the houses sold in autumn on average is about 12% below average, because again, average is 1, and we've got about 0.88 is our seasonal index for autumn. So I can start to see that our values, our house sales in autumn are going to be about 12% below average. Winter's even lower, so that's probably going to be a bit lower below average. And I can see that summer and spring are definitely going to be above average. So you can see how we're kind of going to end up with 2 seasonal indices that are below average and then 2 that are like above average. So it's definitely going to, like, mathematically, it will even out. So they'll all add up to the number 4. And we can always check that if we need to as well. So that's actually all I had for time series analysis. So that was a bit of a crash course and overview. Again, if you have any questions, pop them in the chat. We're doing quite well for time. We have about 45 minutes left. So we'll spend some time doing sequences, maybe a little bit of earth geometry. And if we get any time as well, we might do some exam tips as well. And again, anything we don't get through, it is in the slides down below. So please take a moment to download them when you get a chance. So what are sequences? Sequences are they're just a series of numbers, and they generally follow a pattern, unless of course it's a random sequence, because by definition, a random sequence doesn't really follow a pattern. But sequences, the type that we're looking at, they do follow a pattern. And there's 2 different types of sequences that we're going to be looking at: arithmetic sequences and geometric sequences. So for example, because it follows a pattern, we can predict the terms. So for example, the number pattern, 2, 4, 6, 8, 10. That is a sequence. We've already looked at a sequence together today, because that is a number pattern that follows a sequence. Sorry, a number sequence that follows a pattern. So I started with 2. 2 was my first number. 2 was my first term. And then what did I do to get to my second term? I added 2. And then to get to my third term, or my third number, I added another 2. And then I added another 2. And because it's following this really strong and predictable pattern, I can actually predict the next term by adding another 2, and then adding another 2, and then adding another 2. I can just keep going following this really good pattern. And the awesome thing about it as well is it does come down to substitution into formulas, some of which are on your formula sheet. So again, really super important to be really familiar with your formula sheet, so you know what you need to know how to use, and you know what you need to memorize, because not everything is on your formula sheet. So that's our brief overview of sequences. Let's get into a little bit more terminology. So what I was kind of already introducing you guys to before earlier was the idea of term. I talked about, like, oh hey, our first term, our second term, our third term. What that is referring to is the fact that each number in the sequence is a term. So the first number in the sequence is t1. That's our first term. The second number in the sequence is our second term, so t2. This little n would be 2 in that case. Our third term, our third number would be t3, so n would be equal to 3. And n must always be a whole number. We can't have term 2.5. We can never have that just because it like messes with the rule a little bit, especially when we get into geometric sequences. So here, for example, what term number is term 8? 1, 2, 3, 4. So term 4 or t4 is 8. And another thing I'll draw your attention to is that sometimes t1 is also referred to as a. So that's just another like terminology thing to be aware of. And the last thing you see in this example I gave earlier, 2, 4, 6, 8, 10. The ellipsis means that the sequence goes on indefinitely. So if you want to communicate that the sequence goes on and on and on, which they all do, because again, they follow that predictable pattern, ... implies that it just goes on and on. So arithmetic sequences versus geometric sequences, just to give you kind of like the 1,000-foot overview. Arithmetic sequences are what we just looked at on the previous slide, 2, 4, 6, 8, 10, 12, 14, 16, on and on and on. There are patterns where our rule requires adding the same number each time. Think arithmetic, adding. So our rule could be +5. Our rule could be take 10. It could be +100. It could be -1. And another thing I'll draw your attention to is our starting point could be anything. We could start at 100 and our rule could be -10, in which case our sequence would go 100, 90, 80, 70, ... because it continues. So our arithmetic sequences are like our addition and subtraction. Depending on whether in the rule we're adding or subtracting, will tell us whether like the sequence gets bigger or smaller. But again, it's going to form that like linear pattern because we're changing the exact same amount each time. However, our geometric sequences are the same, similar thing. They're sequences, they follow a pattern or a rule, but the difference is instead of adding like the same thing, which in the case of arithmetic sequences, we call that like the common difference. It's called D. In geometric sequences, we multiply by a common ratio. So we actually end up with like more of an exponential curve, which we'll illustrate a little bit further shortly. So geometric sequences, our starting term might be 3 and our common ratio might be 2. So I start with 3 and I multiply it by 2. So I get 6. I get 6, I multiply it by 2, and then I get 12. Multiply it by 2 to get 24, multiply it by 2 to get 48, multiply it by 2 to get 96, and you can see that every time it's doubling. Whereas our arithmetic sequences grew by the same amount each time, our geometric sequences grow kind of more like exponentially, again, is the word that we're going to use, because we're multiplying by the common ratio every time. So we're going to have a little bit of a look at the difference between those now. So arithmetic sequences, again, the next number can be found by adding the same number to the previous term. And the number that we add again and again and again is the common difference, which is D. And a little side note, D can be positive or negative. So again, our starting point might be 5 and D could be positive 2, in which case our sequence would go 5, 7, 9, 11, 13, ... Or if it's a negative, we're actually going to go backwards. But it's the same process. We're starting at 5, then we're going 3, 1, negative 3, because our common difference is negative. So it's important to keep in mind that our common difference can be positive or negative in arithmetic sequences. So how do we calculate it using recursion? This might look a little bit scary at first, but once we break it down, I promise it'll make a bit more sense. So again, T1, sometimes referred to as A, is the first term in the sequence. And this is the rule that we use to calculate or solve arithmetic sequences using recursion. So Tn plus 1 is equal to Tn plus D. Or if we break it down in words, that can help make it a little bit make more sense as well. So the next term in the sequence, Tn plus 1, is equal to the previous term or the current term plus the common difference. So Think back to our example before, 2, 4, 6, 8, 10. Our term 2, for example, is 4. So if I'm going to say let n equal 2, then we can actually solve that out. T2 plus 1, that gives us T3, is equal to term 2 plus the common difference. That makes like perfect sense. Our next term is found by adding the common difference to our previous term. That's all we're saying here. And we'll do some illustrations to hopefully make that a little bit more clearer. So another thing to keep in mind, and I know this is a lot of new information, so it's okay if you have questions again still, because this is probably quite new content for most of you as well. So if our common difference is positive, the numbers will get larger. That's what I talked about before. It'll get bigger, more positive. And the bigger the common difference is, the faster the growth. So for example, if I'm adding 2 every time, yeah, our growth is going to grow at a constant rate, but like it's still going to be slower. But if I'm adding 100 every time, we're going to grow a lot faster. That's just like how numbers work. And again, this is linear growth because we're starting at a number, adding the exact same amount, adding the exact same amount, adding the exact same amount. It's just going to keep going on forever, really. Because again, we're just adding the same amount over and over and over. And again, that's how we're getting that linear growth in. It's following that same pattern, that same line. On the other hand though, if our common difference is negative, our number will get smaller. And again, the bigger the common difference, the more rapid the decrease will be. And that's linear decay. So that's just some more terminology to keep in mind. And just like the general idea of if it's positive, you know, it's going to keep getting bigger. If it's negative, it's going to keep getting smaller. So we have an example to work through together. Consider the arithmetic sequence defined by T1 equals 3. Our first term, our starting point is 3. And our rule is Tn plus 1 equals Tn plus 4. So our next term, how to find the next term? You take the previous term and you add 4. And we're being asked, what is the fourth term? So I'm going to communicate this really clearly here over to the side in red to kind of illustrate that a bit better. So to substitute, we could say let n equals 1. So now you can see we've got Tn plus 1. But if I'm going to say let n equal 1, we have T1 plus 1, which is T2. And that's equal to Tn. And we've said n is 1. So it's equal to T1 plus 4. So now we can substitute for T1 because we know that our first term is 3. So to find our second term, we take our first term and we just add 4, which gives us 7. But that's only our second term. So if we let n equal 2, we know that our third term is going to be equal to our previous term plus 4, which gets us to 11. And to find our fourth term, we take our third term, add another 4, and it gives us 15. So again, it's just that continual process of this is like the formula to make it like official, but all we're doing is adding 4 each time. We're taking the current number, adding 4 to find the next number. That's what we're doing. Another awesome little calculator trick to keep in mind, to generate a recursive arithmetic sequence using a calculator, what you do is you enter the number. Sorry, this should say enter the number. So you enter your starting point, which could be 5, could be 10, could be 27, whatever your starting number is, you enter that. That's your T1, term 1A starting point, whatever you want to call it. And then you press equals, and then you enter your rule, which because it's an arithmetic sequence, it'll be plus something or minus something. For example, it could be plus 2. And then you press equals, and that'll give you your second term. And because your calculator knows that you want to make a sequence, it's going to keep doing this the more you press enter. So you press enter again to get term 3. You press enter again to get term 4. And you just go on and on and on. And it just, yeah, if you keep track of how many times you've pressed enter, it can help you find like a sequence, like a term further on in the sequence, which is really helpful. So you can also graph arithmetic sequences. So I have 2 examples here. This is my first example. So this one here, T1 is 1. First term is 1. Beautiful. Second term is 3 because every time our common difference is 2, so we're adding 2. So we can see this pattern working out. 1, 3, 5, 7, 9. Similar calculations to what we were doing before, but just in a table form. And it's also been graphed. So this is how we actually graph sequences. So n is normally put along like the x-axis and tn is normally put along the y-axis. Just because like tn depends on n. So that's why we just graph it this way. So when n is equal to 1, our term is 1. When n is equal to 2, our term is 3. When n is equal to 3, we can see that our term is 5. When n is equal to 4, we can see that our term is 7. When n is equal to 5, we can see that our term is 9. So you can see that we graph sequences just like any other set of numbers. Here, for example, our starting point is 9 in this second example, and our common difference is -3. So each time we apply our rule to find our next term, we're actually taking away 3. So we're starting with 9, and then we're taking 3, so we get 6. And then we're taking 3, so we get 3. We take 3 to get to 0, take 3 to get to -3. And we can actually graph that on the same graph. So here you can see when n is equal to 1, our term is 9. So I've graphed that to reflect it. When n is 2, our term is 6. 3, 3, 4 is on 0, and then 5 is actually on -3. And you can also reflect a trend line to suit that. So what differences can you see here? Main thing I notice, or the few things I notice, is that this one, positive common difference, we can actually see that linear growth, same pace, straight line, increasing growth. Here, negative common difference, we can actually see the decay, the linear decay. It's decreasing by the same amount each and every time, which is really, really interesting. The other thing is this, even though there's only a tiny difference, we can see there's a more rapid decrease here because our common difference is bigger. And remember, the bigger the common difference, if it's positive, means it'll grow faster. If it's negative, means it'll decay faster, get smaller faster. So even this small difference of being -3 instead of -2, we can see that that's still influencing our growth. But what if we don't want to do recursion? What if we don't want to find term 1, 2, 3, 4, 5? What if we wanted to skip like straight to term 37? We definitely want to be able to have a much faster way to do that. So a general rule for finding the nth term of a geometric sequence, that's just kind of like the name for it, is the explicit definition, which is this here. So looks a little bit more complicated, but again, once we break it down, it's just a simple matter of like algebra and substitution. So as long as you're carefully showing your work, it should hopefully, as long as you're doing it step by step, you will be able to solve it. So it just takes some practice, which is totally okay. So again, Tn, our term number that we're looking for, is equal to T1, so our first term, plus the number of the term we're looking for, minus 1, multiplied by the common difference. So that's our formula. So if, for example, I'm looking for term 25, I'm going to say let n equal to 25, and as long as I know the right information, then I can actually solve and find my unknown variable. And again, this formula, like conceptually, makes sense in my head because we're saying, okay, the term number I'm looking for, it's equal to term 1, so our starting point, plus this many applications of the common difference. So for example, if we're looking for term 25, I'm saying to find 25, term 25, I'm taking term number 1 and I'm adding my common difference, 25 take 1 time, so 24 times. So I'm taking my term 1 and then I'm adding my common difference 24 times so that I can get to my 25th term. So that's kind of conceptually how I see it. But again, that may or may not make sense in your mind. But as we practice it a little bit more, hopefully the rule will start to make sense in your head. So the common difference for an arithmetic sequence is 16 and term 12 is 236. Find the first term. So here we've jumped straight into a bit of a trickier example, whereas in our example before, the formula is arranged so that we're looking for Tn, our number, but here I've given you our number, it's 236. I want us to find a different unknown. So here we're already using our formula in a little bit more of a complicated way by finding a different unknown. But same step, same process, same algebraic thinking. So Tn is equal to T1 plus bracket and take 1, close bracket, D. That's what we're doing. Always start with what do we know? Substitute in anything we know, and always clearly define all of your variables because part marks for working is so important and so valuable. So make sure you're getting as many part marks as possible. So n is equal to 12. I know that. T12 is equal to 236, so n is 12. I know what term 12 is. And I also know that Tn is 236, and I'm told that common difference is positive 16. So what I can do, substitute in for everything we know. Tn, we know is 236. T1, we actually don't know. We know that n is 12, and we know that d is 16. So now that I've substituted in everything I know, all it simply is solving step by step, following like the regular rules of operations. So again, that's why communication is so important, because if you do make a mistake somewhere along the way, there's still part marks available for like, working out operations and all of those sorts of things. And then again, so what we've done here, we've simplified in the brackets and then we've multiplied there because that's following our order of operations. And then by taking 176 from each side, we can actually find our answer for T1, which is 60. And if we've done that correctly, we'll actually be able to check it, like using our calculator, for example. So if I put 60 equals, and then plus 16 equals would give me term 2, equals would give me term 3. And if I kept going to get to term 12, if we've done this correctly here, that'll give us 236. Just another quick example. So a bakery produces 3 cakes every hour. Initially, there were 17 cakes. If Tn is the number of cakes after n hours, how many hours will it take to produce 300 cakes? So again, it makes, you could use recursion to solve this, but it does also make sense to use our formula. So here, this is actually, in my opinion, where it kind of like sequences gets the trickiest. So T1, I'm actually saying is 20. And that's because, I haven't defined n there, but that's okay. This might seem a little bit counterintuitive, but the interesting thing is, here's where n is defined. If Tn is the number of cakes after n hours, how many hours will it take to produce 300 cakes? But this is really interesting. There were 17 cakes initially. So I had 17 cakes at the start when 0 time had passed. No time has passed, but we still have 17 cakes. But Tn is the number of cakes after n hours. So after 1 hour, we can make an extra 3 cakes. So after 1 hour, we started with 17 cakes and we've made 3 cakes. So T1 is actually 20 because this is saying n is equal to 1. So after 1 hour, we have 20 cakes. Or you could also define T0 as 17. That's another way you can like communicate that. But again, it's really important when it comes to word questions, you need to think about what is it actually asking me and how am I going to communicate it? There are a few different ways you could solve this problem, but you've really got to be careful about what you're actually defining n as. So that's where you need to be really, really careful. So common difference, positive 3. 3 cakes made every hour. And Tn, we want to know when it's going to exceed 300 cakes. So what I've done, I've substituted into my formula. I've expanded my brackets. 3 times n and 3 times negative 1 will give me plus 3n, take 3. And then I've simplified by doing my 20, take away my 3. I've collected like terms. and we want to isolate n. So I've taken away 17 from both sides, and I've divided both sides by 3. So again, isolate n, get n by itself, which has given me n is equal to 94.3. And again, how many hours will it take to produce 300 cakes? That needs to be a whole number because it wants to know how many hours. Remember, n has to be a whole number. It can't really be a decimal. So I'm going to say after 95 hours, that's how long it'll take us to reach the 300 cake threshold. And again, asked in a sentence, always answer in a sentence. It's a great way to, again, make sure you're getting all the marks possible. So the 300th cake will have been produced by the 95th hour. And then you can actually always check by substituting that value for n into your original formula. And I can see here, in fact, that if we let n equal 95, then we can see that after that time that we will have 302 cakes, which means that by 94 hours, we'd only have 299, and that doesn't meet the requirements. So we do indeed have to wait 95 hours to have at least 300 cakes. Our next type of sequence is geometric sequences. So geometric sequences are a sequence in which the next number or the next term can be found by multiplying the previous term by a constant factor. And the factor that we're multiplying by each time is the common ratio. So arithmetic sequences, we were interested in adding the common difference each time, whether it was positive or negative. But here, we're not adding anymore, we're multiplying, and we're not looking at the common difference, we're looking at the common ratio, which is r. So that's our difference with our geometric sequences. So how to calculate geometric sequences using recursion. And again, recursion is that step-by-step process where you find the first term and use that to find the second term. Then you use that to find the third term, and so on. Same thing we have going on here. Our next term is equal to our previous term or our current term multiplied by our common ratio. Again, the factor by which it's growing or reducing each time. And here we have how to calculate our common ratio. So to find the common ratio, again, all we need to really do is solve by saying let n equal, because this will hold true for all of your numbers. But what we're saying here is the common ratio is equal to the next term divided by the previous term, and we'll illustrate that further shortly. So again, when we're calculating geometric sequences, the next term in the sequence is equal to the previous term multiplied by the common ratio. And you can also calculate that using a calculator. What you do is, again, you turn your calculator on, you enter your starting number, or T1, you press enter, then you enter your rule, which will be multiplied by, and then press equals to get term 2, equals to get the next term, and it'll continue on in that pattern. But again, that's a little bit painful, so what if we want to skip straight to a certain term number? This is where we use the nth term or the explicit definition. So Tn is equal to A, which remember, that's the same as T1, our starting point, multiplied by R, our common ratio, to the power of n take 1. Or, like we said, that's putting it into words. But another important thing to keep in mind is we actually don't cover logarithms in general maths. So solving this is actually probably more complicated than it might seem at first. So for geometric sequences, I find most of the time it's easier to use recursion. Or if it is like a bigger number and it is easier to use this formula, I definitely encourage you to use trial and error to find n. So that's actually a valid technique for solving these kind of questions. So if you've substituted in all of your values and you're trying to find n, then the best way to do it is say, let n equal 20. Oh, that's too low. That's not the answer I'm looking for. I'll try something again. Let n equal 30. Oh, no, I'm going to have to try again. So substitution and trial and error is actually completely valid if you're trying to solve for n. If you're trying to solve for Tn, it's a little bit more straightforward, but that's just like a brief overview of our geometric sequences. So again, here are our formulas. We have the next term is equal to the common ratio multiplied by the current term or the previous term. And our R is equal to Tn plus 1 divided by Tn. And we can also use that to find the common ratio, or also check if the sequence is geometric. So again, if we say, for example, if we said let n equal 2, then one way to find r is going to say r equals term 3 divided by term 2. And that'll give you r. Or if you say let n equal 5, it'll be term 6 divided by term 5. And because again we're following a consistent predictable pattern and rule, the gap between each of our numbers is going to be consistent. So this rule, if it is a geometric sequence, will hold up for all of the gaps between all of your numbers. So example here, 2, 16, 18, 54. Is it geometric? Well, we can check that, but I can already see it's not arithmetic because I'm not adding a consistent number each time. So let's check it using our formula. What I'm going to say, like the example I gave before, I'm going to say let n equal 2. So by substituting every time we see an n in our formula, replacing it with 2, we can see that r is equal to t3 divided by t2, and term 3, 1, 2, 3, term 3 divided by term 2 is 18 divided by 6, which gives us 3. So that's our common ratio. And then to properly check if it's geometric, we could check that the gap between these two is also consistent. And then that'll show us if we are following a consistent pattern or rule. So here, for example, n, we're looking at terms 1, term 2, 3, 4, and 5. So here our rule, our starting point is 1, and our common ratio is 2. So we're multiplying by 2 each time. So doubling, 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 doubling. That's what's happening here in this geometric sequence. Here, I've added in an arithmetic sequence. So I've got t1 equals 1, and I've also got, so again, same starting point. They're both starting at 1, but this is multiplying by 2 every time, but this is adding 2 every time. So geometric, arithmetic. And I've color-coded them to hopefully make it a little bit more clearer. So again, you can see this is doubling every time. It's getting much bigger. This is just adding 2 every time. So those are our two different types of sequences. And we can actually graph them on the same graph to compare them. So this graph in blue, you can see this is our geometric sequence that's been graphed. You can kind of start to see it's forming that exponential curve or pattern. So again, we're multiplying every time. We're getting bigger by a certain factor, not just the same number. And again, our Tn depends on the term number. So again, that's just getting into the formalities of why we graph n on this axis and Tn on this axis. As long as you remember to graph n on the bottom, that's awesome. That's all you need to make sure that you're doing. So let's graph our arithmetic sequence. Here, you can see I've placed my first red marker because term 1 in our first one is 1. Term 1 in our second one is also 1. Still the same. Our term 2 here is 3. Oh, so it's actually a little bit bigger than our other one here. But then let's see, our term 3 is 5. Still a little bit bigger. Our next term is equal to 7. Next one is equal to 9. So now all of a sudden, we can really start to see this pattern coming into play. And you can see here, I've graphed our, it's way off the graph, but I've graphed our potential next term in our geometric sequences, term 6, 32, and this is our next term in our arithmetic sequence, 9, and then adding 2 to get to 11. So we've got 9 here, and then we add to 11. So you can start to see that they're fairly similar in the early stages here, but you can see that my geometric sequence is really getting exponentially bigger. It's following that exponential curve, while our arithmetic sequences are going to follow that same linear trend forever if we keep our sequence going indefinitely. So you can start to see just how different our arithmetic and our geometric sequences are, and when you graph that, you really start to see the pattern. So again, exponential growth is what we see in sequences, but we see that when r is greater than 1. That's when we see our exponential growth. For example, a practical application of that is if we're modeling compound interest. The amount in our bank should hopefully be getting bigger by a certain factor of this amount, this r, each time the interest is applied. The other side of things is when r is less than 1, and we actually see like that exponential decay or depreciation. So with arithmetic sequences, if we have a positive common difference, we kind of like add 4. And if it's a negative, we might like take 5. To model the inverse of like exponential growth, we don't typically do like divide by this, although you totally could to model that. What we normally do is we still multiply it, but we multiply it by an r value that's less than 1. So for example, if I multiply it by 0.5, that's halving it. It's the exact same thing as dividing by 2, but we're just multiplying it by 0.5. So again, that's to illustrate that when r is less than 1, we'll see exponential decay. So for example, if something depreciates by 25% every year, it's becoming worth 75% of what it used to be worth. So our common ratio is 0.75. So whatever our amount is, we'll start at that amount and then we'll multiply it by 0.75 to model that it's depreciating by 25%. And then the year after, again, it'll decrease by a factor of 25%. So it's going to be decreasing, but again, it's going to be forming that exponential curve. So yeah, that's kind of in essence the difference between our exponential growth and our exponential decay. Last kind of thing I'll draw your attention to is the fact that exponential decay is again that like geometric sequence when r is less than 1. And we'll kind of start like, it might start at this value and then it might lose 25%, lose. And it'll keep kind of, losing that value, but still making an exponential curve. But when we have straight line depreciation, that's modeled by arithmetic sequences, because again, straight line depreciation is where we're losing the exact same amount each time period. So it might be like take 4 each period. Eventually, we're going to reach 0. Whereas in geometric sequences or exponential decay, we technically actually don't ever reach 0 because it's just constantly being multiplied by 0.5. So it'll forever get smaller and smaller, but will never actually technically reach 0, which is interesting. And again, straight line depreciation is modeled by arithmetic sequences where the common difference is a negative number. So a geometric sequence example, a newly manufactured car is priced at $24,000. Each year, the car depreciates by 25%. Write a recurrence relation to model this scenario. And this is the answer that we have here. So again, this is a little bit similar in some ways to our cake scenario because n here is how much the car is depreciated or the car's depreciation after 1 year. But the newly manufactured car, when it's 0 years old, is 24,000. So that's really interesting. So T0, n is equal to 0. When 0 time has passed, it's worth 24,000. And we'd actually have to use our formula to calculate how much it would be worth after 1 year if we wanted to. And then our formula is, again, Tn plus 1 is equal to r, common ratio, 0.75, multiplied by Tn. And then that's the rough mark breakdown for that one. And then we could actually use this formula to calculate how much the car would be worth after 4 years. So, for example, T1, we're going to let n equal 0. So T0 plus 1, or down here, T0 plus 1 is equal to T1 is equal to 0.75 by T0. So that's the value of our brand new car. So what we're saying here, again, to break it down, after 1 year, so after 1 year has passed, our car is worth 75% of what it used to be. So that 75% times its original value gets us the next value of $18,000. Our car is dropped in value by $6,000 in a year. That's how much it's depreciated by. T2, same thing, except now we're doing, well, okay, after 2 years, it'll be worth 75% of what it was worth after 1 year. So we're going to do 75% times the value after 1 year, 13,500. Our car's dropped in value by $4,500. It's still dropping in value by 25%, but the amount that's dropping is less each time because it's a percentage, not a set number. same for term 3, and same for term 4. And then asked in a sentence, answer in a sentence. Make sure you're getting all of those marks. So therefore, after 4 years, the car will be worth approximately $7,593.75. Amazing. So that is an overview of our sequences. We only have like 5 or so minutes left. So I'm just going to quickly go through a few key ideas for earth geometry and then a few final exam tips if we get quick time to really quickly. So because the earth is very close to being a sphere, we can actually mathematically calculate time zones, distances between areas, and all of that kind of thing. So when you're getting an introduction to earth geometry, think latitude and longitude, which is like that global positioning system we use for like any point on the earth can be defined by where it is in relation to latitude and longitude. So think about the earth. See if I have a diagram. Awesome. So think about the earth. We know it's like roughly a sphere. So in the earth, we can have great circles and small circles. Just terminology wise, great circles are a cross section where the radius is equal to that of the sphere. So pretty much the largest flat slice possible. Whereas small circles, like our blue example here, are any circle with a radius less than that of the sphere. And just to quickly illustrate, lines of latitude, and again, this is a very brief introduction, so don't stress if it doesn't make the most sense, but lines of latitude are small circles that run parallel to the equator. So think of this like the earth, and think about all these circles that are running all the way around the world. And then the equator is a great circle because it's like the really big circle around like the widest bit of the earth. And then all the small circles keep running down until we get to the South Pole. The main takeaway that I want you to have from this is that these like circles, they tell you how far north a point is from the equator. So here we have the equator, and we can use these circles to measure how far north a point is on any point in the earth, or we can use them to measure how far south we are from the equator. Longitude is the opposite. Longitude is how we measure how far east or west we are of the prime meridian, which is like this just like imaginary line. It's kind of like the equator, but for like up and down. So don't stress too much about that though. But the main thing I want you to take away is that latitude, we're measuring how far north or south something is from the equator. And then longitude, we're measuring how far east or west a point is. How I remember that is I think like longitude, these are our longer circles. So these are like our semi-great circles that are running all around the world. So we have 0 degrees, we go around all the way around to 180 degrees east and all the way around to 180 degrees west. And you can see that illustrated here a little bit more. So again, we're thinking latitude measures how far north or south we are, and longitude measures how far east or west we are. So for every point on the earth, it can be like defined by where it is in terms of latitude and longitude, like that diagram shows there. And latitude always comes first, so how far north or south it is, and then we write longitude, so how far east or west it is. How I remember that is latitude comes first alphabetically, so we put it first in the coordinate order. That's how I remember it. So it's how far north or south, and then how far east or west. Again, we can talk about like the position of Brisbane, and all these different things. Also, what you'll be looking at once you get more time to cover it in class is looking at earth geometry with when we're looking at the distance between points. The biggest takeaway that I want you to take away from here is that we use a different formula depending on whether they're on the same longitude or the same latitude. And once you cover this in class a little bit more, it'll make a little bit more sense. So again, all of these slides are available from the resources tab below. So I'm just quickly flicking through them now to make sure there's nothing else I want to highlight. But in essence, we are unfortunately out of time for these. But again, they're in the resources tab below. So if you would like to go through them in your own time, there's lots of information on there. So it should hopefully still able to be of some help for you. In our last kind of few minutes together, my few really brief exam tips for you. First one is preparing for externals in particular, or even your internal assessment. My tips for that is come up with a study plan, focus on your areas of weakness, identify where you need to spend more time, come up with a timeline. My second bit of advice is plan with your external exam timetable in mind. Once it's released, highlight it, take into account how your exams are spaced, because that's going to influence your study time. Also, get into good habits early. I know so many people, they're like, oh no, I'll start studying tomorrow, I'll start studying next year. Tomorrow never comes, so get into good habits now. Start of the year, coming into year 12, perfect time to get into those good habits. And also stay on top of content as you go, so that when it gets to the end of the year, you're only revising, not learning from scratch. The other thing, be familiar with your formula sheet. Like I've said before, you need to know what's on it so that you know how to use it and what you need to memorize. And lastly, in the external, make the most of perusal. Start with questions you feel most comfortable with. Break it down. If you're stuck on a question, skip it and come back to it. Sometimes something will just like click in your brain, and it can be, it's better not to waste time if you don't know if you're going to be able to do the question. It's better to do questions you know you can do and like be banking those marks. And again, if you're stuck, write down everything you can think of. Formulas, define the variables, rewrite the question, answer in full sentences. Sometimes you can still get part marks even if you have absolutely no idea what the question is about. And at the end of externals, make sure you actually celebrate your hard work. It is a very big accomplishment to finish year 12. And you guys are almost there, which is so exciting. So that is all we have time for today. I just want to say a massive thank you for joining us, and I hope this was helpful. Remember, you can rewatch this lecture, go over the slides at your own pace, and all of those things are available for you as well. So I just want to wish you the best of luck as you continue with your year 12 studies and progress throughout the year. Maybe I'll see you around at another lecture later throughout the year. But thank you so much for joining us, and best of luck with your studies. Thanks, year 12s.